excess of millimeter emission on the snow line, let's say on the CO snow line, was related to the discussion that Phil had on the accumulation of solids at that point. I think I would be cautious at this time. I mean, what I wanted to highlight this morning is that we are almost there to have the sensitivity and angular resolution to do this type of measurements. There is indication in this system that there is excess emission at the right position and the millimeter. It has already been observed in the mid-infrared, which means that there was there is something in the atmosphere of the disk, in the change of curvature or something like that. The fact that we observe excess emission in the millimeter, which in that case is 850 microns, might be related to two things, I think. The two plausible explanations are that either there is an increase in density, but it has to be a fairly large increase, which we haven't calculated yet the details, but it's not a minor disturbance in that case, or a local increase in the temperature, which was another thing that Phil mentioned, because the emission at millimeter wavelengths is directly proportional to the temperature. So if you increase the temperature, say, by 30% locally, then your emission immediately increased by 30% locally, okay? Or a factor of 2. A factor of 2 is big. So that, observationally, I mean, this is tentative evidence so far. There might be something. It needs to be confirmed and studied better to make sure what it is. You want to say something? No. Okay. That sounds good. Nice escape. Nice escape. Also don't say.
So the first question is, first of all, I was hoping to hear something on the current observational understanding on what the magnetic field strengths and topologies are in these systems that we see out there. I seem to vaguely recall a Nature paper from sometime last year where I don't know who, I can't remember the authors, but what I do remember, or at least I think I remember, is that they reported polarization measurements of magnetic field strengths and topology of HL tau, and they suggested that most systems have predominantly toroidal, predominantly toroidal field configurations. So the first question is that the case? Is that really the case? What do we think the field topologies of most protostellar disks are? On the other hand, Phil was talking today morning about the Blandford Payne mechanism, which seems to be the best candidate we have to explain strong collimated outflows. Now this model also requires there to be strong long-range poloidal fields. Now, if this is indeed the case, would this how would this work if it turns out that most T-Tauri disks or protostellar disks have predominantly toroidal fields? And the final bit to the question is, how would the field geometries determine the accretion processes of planetesimal formation processes in such disks?
Who wants it?
Who wants to start?
Okay, well, start with. Okay, so maybe to start with the second question, I think even if the poloidal field plays a dominant role in, if you like, determining how much accretion there is, and also how much potential outflow there is, that doesn't change the fact that the dominant field component will still be the toroidal field, because the shear in the disk is always going to be the fastest process. So I think from an observational point of view, what one should certainly expect to see the toroidal component be dominant. And actually, I think my recollection of the HL Tau paper was that part of the puzzle there was that it wasn't entirely a toroidal field. They were finding it was some more complicated geometry, which I think would be quite hard to would be quite hard to understand. I remember other parts of the question. In terms of what you expect, I mean, I think one aspect is that if you go back to the earlier stages of star formation, one of the plausible ways of averting a magnetic braking catastrophe is to have magnetic fields that are actually not aligned with the disk rotation. So perhaps if you look at sufficiently young systems, you might see on large scale some evidence for that in those systems that have actually managed to form disks.
Non-axisymmetric perturbations can lead to the MRI if the field is also purely toroidal. This is something I think most people seem to overlook, or at least most theoretical papers on disk accretion that come out, especially in the context of protoplanetary disks, always start with let's stick a poloidal field in there, and then let's see how the MRI comes about. But it really isn't necessary that there be a poloidal field for the MRI to show up, is there?
Yeah, so it's definitely the case that the MRI doesn't require any poloidal field. I think the sort of new thing is that actually until recently it was quite difficult to do simulations that had a poloidal field. So there's been a lot of focus recently on simulations with a poloidal field, just because those were not possible before. Where I think you need the poloidal field is if you have some significant, say, ambipolar damping, because then if you don't have that, if you just start with purely toroidal fields, you probably end up with quite weak accretion.
Observations. Okay, so on the observations, yes, I didn't present anything on the measurements of the magnetic field. This is obviously one of the great things that we want to understand. I mean, the magnetic fields in star formation and in the disks also. Regarding the HL tau, if I recall correctly, the problem there is always whether you are really observing the disk or you are really observing a contamination from the envelope, which might explain the fact that you have a strange geometry in the flow, in the field lines. Sorry. The way we do these measurements normally is, as you said, through the polarization, which essentially implies that we assume that grains are not spherical, that they are elongated, and they are statistically aligned with the magnetic field. And then by observing the linear polarization, we infer essentially an orientation of the grains that we think is related to the magnetic field direction. That's typically the measurements that we do in continuum and in the dust. There are upper limits of measurements in disks, in real disks, not HL tau, that is a young object. In more evolved disks, there are upper limits. And we are all waiting for ALMA measurements. And polarization is something that we will start to do next year, starting already the observations, but we will start. Results will come in the next year or so. It's difficult because the fraction of polarization that you expect is small, and so it's not easy to do the measurement. Another measurement that we hope to be able to do is the Zeeman splitting in the molecular lines, but there on the disks at the angular resolution that you require probably is going to be very difficult to do. So at the beginning we will do, and in fact with ALMA we are not yet offering spectral line polarization because it's more complicated than continuum polarization. You have to do more complicated calibrations. But this is something that we always wanted to do, so it will come because clearly magnetic field is still a big unknown, no, in the entire field of star formation. From the I mean, it's expected to play a dominant role, but the real measurements are really scant at the moment. So it's obviously one of the key things of the future.
So I think there was a third question you were directing to me, the influence of magnetic fields onto planetesimal formation. I think when you have reached a certain size of objects, when you have grown beyond the dust size, then I think magnetic fields will not play a major role anymore. You are basically decoupled from the magnetic fields because it's not imaginable that these particles have rather large charges or something, or magnetic fields in those stages. I think in the early phases, of course, you have the MRI turbulence that Phil has talked about, and there, of course, the collection of particles in the turbulent eddies that will enhance the growth has a direct influence on the growth time of the planetesimals, and then by that process, as I've shown and also Phil has mentioned, is that you can directly cross the meter barrier of particles and go directly from very small grains, dust particles, to larger sort of sub-Ceres size object. Yeah, this is one way. So this is where the magnetic field helps, but in general, I think there are also other sort of turbulence fluctuations will help there, vortices and turbulent eddies and so on. And there have been some experiments, in fact, that with dust particles that were charged by the Braunschweig group. So does the charge on dust particles make a major difference? And I can't recall any specifics of their results, but talking to Jürgen, Blum, and others, there was always the statement made that it does not really make much of a difference. So charges of charged dust grows with the same under the same conditions as non-charged dust, apparently. Shall we give them the?
I was wondering if you could comment on the ratios in context of
So the question was, what information can we take from the D/H ratios in the context of the Nice and Grant tech model? Okay, if you look, I mean, this I think reflects to the question of how the water came to the Earth, and we have seen in these simulations here that in the Grant tech model, when the planets move out, you can deposit huge amounts of water from the outer solar system basically into the inner solar system and deposit that on Earth. The question is whether this is then in the early phase evaporating again, because the Earth in that phase was hot. Yes, it was probably molten at that time. So it was the idea is that the Earth might have been in a molten state for the first 700 million years when the LHB occurred also. So there's apparently some coincidence in the ages of the oldest stones on Earth and the occurrence of the LHB. I don't know whether this is a real connection there or not, but some people discuss that. So and then the LHB itself might have also kept the Earth also hot. So it's not quite clear what happened to the water there, which was delivered from the outer solar system. And I don't know presently I mean, comets coming from that region have typically, I think, a different composition there. There's one comet which has a similar composition, Hartley, this famous comet which was mentioned, I think, by you also, and which has surprisingly the same D/H ratio, but the predominant idea presently is that the water comes from a region of the outer asteroid belt, basically, between Mars and Jupiter. I think this is the preferred region where the water of the Earth comes from, and this comes, as I've mentioned in passing, also from other recent observation that the water that you have, or the D/H ratio in chondrites that come from the Vesta group, have the same ratio as you find on Earth. So this and other chondritic material has also the same ratio of not only D/H, also other isotopic ratios, which I can't recall now. I think N14. Sorry?
Nitrogen
yes.
14, 15.
Yeah, exactly. So they have the same isotopic abundance ratios in different elements, and I think this is a stronger indication that we got a rather large influx of material from that region there.
So my question is this one: how the study of exoplanetary atmospheres, such as measuring composition, abundances, or rotation, whatever, can constrain the formation of a planetary system or disk line or whatever?
Who wants to answer?
try first.
The question is, if we observe, let's say, that were physical properties, yeah, if we observe physical properties of extrasolar planets, and you mentioned atmospheric, spherical composition, rotation, and also not orbital properties. I mean, mass radius relation, those kind of things. Yes. The atmospheric composition of these objects. I mean, there's the idea, I think, that you can couple the compositional evolution of exoplanets together with the population synthesis model. So this is the next step, and I think was mentioned also on the last slide there. And I think was it Jan came up also and said, okay, this is now the next step that people want to do. You see, if you know from your history of formation of a planetary system the evolution it has taken through the disk, then you know where it has accreted how much material. Then you can look what you might expect and then try to observe this also in these exoplanets. Yeah, so just the other day, I think Kevin Heng today or yesterday submitted 2 papers that they have discovered apparently sodium in exoplanets, in the atmospheres. Oh yeah, so you know everything. So why do you ask? So anyhow, so they are apparently very new papers out, and the question is then: is there a preferred location in the disk where you might have collected these special materials there? But I'm not an expert in this. The expert is standing there with a microphone, who could say more about this. Whether it's really possible to pin it down. I mean, elements that you collect, in the way out from outside in, they tend to settle also in the atmospheres. Yeah, so you might lose, in fact, some of the information that you had initially on its way inward. Yes, what elements were there?
And perhaps slightly related to this. I mean, I think there are certainly some planets for where there is extra information that does pin down something extra about the formation. I mean, one thinks, for example, of the subset of hot Jupiters that are actually too small compared to sort of standard theoretical models, where clearly there's a good explanation there that maybe that points to very large core masses, which certainly are quite interesting from the point of view of understanding the range of core accretion conditions. And likewise, perhaps some small planets where there's very high densities, which maybe are more comparable to Mercury type systems in the solar system. And since we certainly have plenty of trouble understanding the formation of Mercury, understanding those objects potentially gives us, I think, some interesting information. In the other direction, clearly with only very limited atmospheric information, there seems to be, my impression at least, is there's generally a fair amount of degeneracy in terms of what structures and true compositions are really being seen. But maybe that will change when that the data is larger than it is currently.
Maybe I can comment on this because you speak with the microphone. I can't speak with the microphone. The other one. So just a comment on what you said, Willy. So first, it's not to be done. We started to couple population synthesis and composition, and Amaury left, but it's his birthday today, by the way. But he left, but he submitted a paper that was on AstroPH, I think, in January. So there are computation where you compute the C2O ratio coming from population synthesis and formation models. But I think the point that is very important is the one you said. We can compute what is the global composition of a planet, but now knowing what is in the atmosphere and in the core, this is another difficulty, and it's, I think, the major problem we have now.
In the protoplanetary disk, because the reason I'm asking is because if charged lightnings occur, that can also explain the chondrules formation, right? So do you think that is possible?
Maybe let me just say something about the last part, right? I mean, I think it may be there's certainly some discussion I've seen about possible discharge mechanisms in the protoplanetary disk. Colin McNally, for example, has discussed this recently, and I think those are quite interesting and possibly important processes that might be taking place. I think in terms of the specific application to chondrules, my impression, this is not something I've ever worked on, is that there is a reasonable chemical argument that says that the region of the disk that has to be heated in chondrule forming events has to be quite large, and that's based, for example, on the amount of sulfur that is seen retained in chondrules. So the idea that chondrules are predominantly formed by very localized heating processes, which would be the lightning bolt hypothesis, I think probably has some reasonably clear observational or experimental evidence against it. That's not to say that there isn't lightning in disks, but just that probably it doesn't play a dominant role in that particular application.
We know that in the solar system there are several big satellites, for example the moon or around the giant planets, and well, as of now we have not detected any satellite around exoplanets nor double planets, which constraints this non-detection or possible future detection would add to planet satellite formation.
So the question relates I think, presently non-detection of satellites around exoplanets to something like their likelihood or so, if I understood this correctly. How likely is it that you can make moons around exoplanets, and what does the present observation situation tell us about it? Okay, you're right. I mean, they haven't been detected, and I don't know how close we are in doing so. There are some attempts there in looking, I think, at what it is, the TTVs or so that might occur then. But the TTVs need a rather massive moon, I think. I'm not an expert there as well, but I could imagine if you want to detect time variations in the transits there, that you need a rather massive moon like the Earth-Moon system there. And this is rather extraordinary already in the solar system. Yeah, this is very clear. And the question is, how often you have moons around planets. I think all the major planets, I mean the bigger planets in the solar system have significant number of moons, so this is a very likely process to have, obviously. And the question will thus be, I think, coming back to the first part of the answer, how likely is it that we observe, let's say, the moon with that mass ratio that we have in the solar system, major planets, if that would exist also in the exoplanetary systems, how likely would it be that, what is the possibility that we could observe such a moon? I think there's an observational limit there that means below a certain mass you will not be able to go. But I think this is just presently, I think, we cannot really say anything about this since we have no samples whatsoever. If we have observed one and we know how it is, then we could begin studying this. As now I would think it's a generic process, yes, and you could have many moons around those planets.
So I think I would certainly agree with that. I mean, we would certainly expect it to be shocking if there weren't both regular and irregular satellites around exoplanets. My impression indeed is that the current observational limits really just exclude very massive moons that wouldn't have analogs in the solar system. So perhaps this is just an encouraging case where the immediate observations have not directly contradicted what we would expect theoretically, because we'd actually expect smaller moons, and hopefully those will be discovered soon.
Just what I wanted to add, that from the ALMA perspective, obviously, we do have now, we do have now the sensitivity to try and detect circumplanetary disks around young planets, not forming planets, if you think that satellites form that way, which may not be the case. So there will be measurements coming out in the next 1 or 2 years with the first of this type of measurements. The one that I know of is an upper limit in the sense that that is just one case. There is one case that we have observed, and we do have a very strong upper limit in the sense that that young planet would not be able to form the system that Jupiter has, just for reference. So it does not have a circumplanetary disk that is as massive as what you expect to form the Galilean satellites, for example. Okay, and that particular object is young, is still young. So the primary still has an inner disk. So either has formed them already, or it does not form it that way.
I can make one more comment here, that we have just been informed on this sheet of paper here, transmitted to us, that there's today a paper out apparently on exomoons by Kipling or somebody, just today on Astropage.
Well, I think there's certainly. Sorry. Yeah. So the question was about circumplanetary disk models and their relationship to the formation of the regular satellites of Jupiter and Saturn. So I think, obviously the major uncertainty, or a major uncertainty, comes about from the fact that the regular satellites of Jupiter have a very different structure to the regular satellites of Saturn, right? In the case of Jupiter, we have 4 massive satellites. In the case of Saturn, a lot of the mass is really just in Titan. So, what that really implies for satellite formation is not really clear to me. And so certainly there are other models which are really quite different, particularly that have been proposed for the Saturn system. I think what's known is that a reasonable amount is known about the dynamics of satellite formation and how that would differ from regular planet formation. For example, you need a different amount of gravitational focusing and things like that. But the issues of migration, which we heard about in the context of planet formation, which are difficult there, those also play presumably a large role in the formation of the regular satellites. And I think probably there's enough uncertainty in our understanding of migration in that environment that I'm not completely sure we should really, it's really a very open question to my mind, how much we should trust the existing models that have been put out there for regular satellite formation. It will, I think, in general, be hotter than the circumstellar disk at that location, because you'll basically have the contribution from stellar heating will still be there, and then potentially, unless the disk is very dead, there could be a significant accretional component. And so it will depend very much on this issue, which really emphasizes very uncertain about how much mass really goes from the protoplanetary disk to the the satellite disk, and how fast that flows, because certainly some of the simulations suggest very high mass flow rates, which would imply that the circumplanetary disk was actually quite thick and had very significant viscous heating.
Is there another question, remark, thinking, or whatever?
Here, micro.
Just regarding the alpha viscosity that we saw that in the models were used, that how is it done from observations? How well can be constrained from observations?
Alpha viscosity.
Good. That's fine. That's an easy way out. So Well, I think that we have two. Oh, yeah, sorry, yes. The question is how we can constrain the viscosity observationally, if I understand correctly, in the disk. And so far, as I said, we have two measurements based on integrated line profile, so fitting a model of a disk to an integrated line profile, and essentially trying to put limits on the non-thermal broadening of the line, which we think is related to turbulence, and we think that turbulence is then related, or we can relate this additional broadening to alpha. This is a global measurement, and it's just a measurement of turbulence at this stage, so the line broadening. As both Phil and I showed, we think that with ALMA we will be able to actually measure as a function of position in the disk this non-thermal line broadening, and that is again one of the big things that we want to measure with ALMA, because that obviously is a big uncertainty in the models, as you know. I mean, do you want to add anything?
No, I can just add a speculation. I was just thinking, because if you think about measurements of alpha, I only remember the famous disks in cataclysmic binaries. And there you can infer, or can get some direct, indirect, let's say, measurements of the viscosity from the decline from the outburst. You see, they go in outbursts, they have a rise, 5 magnitudes, and then they fall off on a time scale of, let's say, weeks or so, they fall off. Or less than a week, and from this time scale and the radial range which is covered there, the disk size in these cataclysmic binary stars. From there you can get some information on the magnitude of the viscosity. So if you had some time varying processes in accretion disks like outbursts, XORs or something, or even FOURIER outbursts or so, they from the decline phase, possibly, if you know the radial range which is covered in this decline phase, this is more a speculation now. Maybe it's possible to infer something from there, but I don't know if anybody has done this. This is not a real, let's say, solidified comment here.
So the question is whether we expect, from a theoretical point of view, to see binary planets. I think so one class of things that might be close to binary planets might be more extreme versions of the Earth-Moon system, right? And so I think that formation channel seems quite plausible, right? There's no particular reason that the Moon is the upper limit for the size of a satellite you could form that way. I think generally it's quite hard to imagine forming binary giant planets, simply because at early times those objects are going to be large, and so it's quite difficult to imagine, if you like, what you would need is some sort of tidal capture mechanism, and the parameter space, I think, for that to happen, given realistic encounter velocities, is probably quite small. I would be delighted to be surprised, and I wouldn't really be surprised to be surprised. But from a theoretical point of view, I think forming really binary giant planets is probably quite difficult.
Jan, here.
Okay.
Okay, so the question was this idea of measuring the turbulence from molecular line widths, whether we can say anything radially, and sort of irrespective of that, whether we can really trace that measurement to a measurement of alpha rather than just some other turbulence within the disk. Well, I think obviously for the moment, the measurements are extremely preliminary, and so it's probably another year before we'll have reliable measurements. So I think first of all, we'd like to just have any measurement that we could really trust, and then move beyond that perhaps to look at the radial dependence. The quantity that we expect to be able to measure most reliably, I think, as was discussed, is actually the vertical dependence of turbulence, because you should be able to look at different species that probe different layers of the disk. But I think, for the moment, and maybe for a long time, really we are just going to be measuring velocities. And so we're not going to be measuring velocity correlations, which would really be directly the Reynolds stress, never mind the fact that potentially there's magnetic stresses there as well. And so in particular, when you look at lines that are quite optically thick, and you're looking really at the surface of the disk, then actually what you're probably mostly seeing is waves that are generated in the midplane and have steepened to become transonic. So, from a purely observational point of view, there's a lot of ambiguity there. What one might hope is that you can compare that against theoretical models, and if they agree, you might have some more confidence that really, we understand something about turbulence. If they don't agree, then you've learned something interesting as well.
Since we talked about exomoons and binary planets, for a third category of the maybe more exotic free-floating planets, you guys have any thoughts on those and formation mechanisms? If they're out there, they probably form disks and would be ejected. The formation mechanisms.
You want to say?
Yes, then you. And first the observational part, and then I'll let it to you to comment on the thing. So basically, the question is, what about free-floating planets and their formation mechanism? I think that one of the things that I think everybody expects is that these dynamical ejection processes become relevant at low masses. So you do expect that a fraction of these objects at low masses can be ejected from a system, so forming like a planet. The way we try to trace this observationally is to try to basically trace the disk properties with the mass of these young objects toward the bottom of the IMF, essentially, and try to see whether the disk properties are similar or whether they are significant. There is a significant change in the disk properties that might be related to an ejection process. The preliminary result indeed suggests that the disk masses and possibly sizes are smaller as you go deep into the brown dwarf regime, the young brown dwarf regime. So indeed, there might be a possibility that some of these free-floating objects are actually not born with their own little core, with their own little disk, but they are actually formed as part of a multiple system or in a fragmentation in a disk and then ejected.
Yeah, I think it's a difficult question. I can follow also what Leonardo said. I think it's very difficult to say if you just observe now objects which are in the planetary mass range, where they come from, whether they have formed like a star formation through a star formation mechanism and then have been scattered out in the early phases in a cluster environment, for example, or whether they have formed through a planet formation scenario in a disk around a star. But I think this is something maybe could start up a discussion. I mean, there is nothing like a free-floating planet, okay? A planet, by definition, as we know from the ALU, is orbiting a star. And so it cannot be free-floating, okay? So, and this is the point. I mean, a planet, as many people think, is a planet if it formed in a disk around a star. Yeah, and this is, but a planet is something which is still, let's say, connected to a star and orbits the star. But this is more, let's say, a definition, point of view, and not really an explanation to anything there. But it's quite clear from what we have been discussing in the last few days, you can form these objects, I mean, in either way. It's very likely if you have a few massive planets in orbiting a star, and then you compress them by some mechanism, convergent migration or something, then they interact gravitationally, they scatter each other. One of these objects becomes a highly inclined hot Jupiter, the other one becomes on a large, let's say, eccentric orbit, and the third one is thrown out. So this is a configuration which is very likely also to happen. I mean, it's nothing unusual, so you can easily produce objects which are, let's say, not bound to the initial system anymore, I think.
Maybe I'll just add one dynamical point to that, which is that trajectories that actually eject a planet from a planetary system in one go, a giant planet, are fairly special, right? So you can do that with spacecraft, but most ejections take place via first the planet becoming extremely eccentric. So sort of prediction of the models that predict a lot of ejected planets floating there is that there should also be a population of bound planets that are really on very, very eccentric orbits. And so, in principle, at young ages, 10 to 100 million years, you might expect there to be at least some objects out there at 1,000 AU with, eccentricities of 0.99. And so there are some perhaps observational ways of sort of testing how many planets are in the process of being ejected.
Something. I'm not sure. I'm not a major expert of these searches of planets around brown dwarfs. So obviously, So the question is whether there are population of planets around brown dwarfs, whether there is there is a deficit, and why there should be a deficit there. I am not an expert of this, so I don't know the statistics of planet detections around old brown dwarfs, let's put it this way. So really looking at the planet. Looking at the disks around brown dwarfs, there are several studies that actually suggest that forming Jupiter-like planets is extremely difficult because you don't have much mass in a disk around a brown dwarf. The mass of the disk scales down, and so you expect that it's difficult to form massive planets around brown dwarfs. So I would expect that you would expect to have not very massive planets, and so maybe there could be a bias in detecting them, but I'm not sure about this.
Okay, so this is a difficult enough question, and I'm just going to completely ignore it and answer, say something different. But one thing that is somewhat related to the question, of course, is that when you get down to brown dwarfs, the mass ratio that would be implied for gas giant planets is then much closer to equality than it is for regular stars. So, clearly, even if we see gas giant type objects around brown dwarfs, there's a much bigger question about the formation channel there than there is for the stellar case. But then, in a sort of more general point, I think there are stages, as we've discussed this week, of the planet formation process that are potentially yes/no items, right? And in particular, getting past this meter barrier and forming planetesimals, requires we think at least a sort of non-trivial set of conditions. So it may be that there really are some class of disks, which might be related to the stellar mass or the metallicity or whatever, that really are unable to form planetesimals at all. And for the moment, there's not really any clear sign in the observations of that process, basically because planets are so common, it seems, around stellar mass objects. But actually it would be very interesting theoretically if we could find some stars that we could really say don't have planets at all, because that might give some clue about those threshold processes that could be at work.
If I briefly follow up on this, indeed there is only one case. I mean, there is one case I'm aware of a brown dwarf with a massive companion, with a lower mass companion, obviously, than the brown dwarf, which is 5 Jupiter mass, more or less. I think I showed that at some point. And actually, as Phil said, we think that this is a binary system rather than a planet-star system. Okay, so the formation mechanism may be different than what we think. The thing that is that we were surprised when we tried. I mean, we were looking at this grain growth in the earliest phase, so before forming planetesimals. So the growth of grains to millimeter size. We weren't expecting it to find it in brown dwarf disks, because the average densities that we were expecting for those disks would have not allowed efficient growth of millimeter-sized grains, okay? And instead, we do find a signature in all the systems that we looked at, that at the moment are relatively few and probably massive, so it's biased a little bit, the sample. But we do find evidence, I didn't have time to show this, we do find evidence for significant grain growth also in these extremely low mass disks. So this is a thing that we were surprised when we found, because it was not predicted directly by the models. And why is that? It's a good speculation, but I don't have an answer.
Yes, the question is, I mean, we have heard something now about the structure and the Kuiper belt around the solar system, and what do we know about the structure of the Kuiper belt in other planetary systems or around other stars in general? I mean, I have to admit I'm not really an expert on this, but there are certain structures in debris disks that can be observed. But there are some non-axisymmetric features there. There are some warps in debris disks which can be observed. For example, Beta Pictoris is one of the famous examples which pictures have been shown for Beta Pic, and there was already known that there is some warping in these disks there even before people have detected the planet, and they have inferred from the types of warps that have been observed in these disks that there might be a planet present. So this is the idea. You have a large scale. I mean, you will not be able to observe very small scales there, but from the large scale disturbances, let's say non-axisymmetric features and warps, you can always think about the presence of a planet which may create such features there. But I am not enough of an observer now to tell you exactly in what systems this has been done and in what systems this has not been done.
So from the observational point of view, observing Kuiper belt objects in other stars, even as a collective, is difficult. It's difficult because they don't admit that much, even as a collective. So what can be observed is dust, obviously, because the dust is, so the observation of debris disks that I showed today were mostly dust. Okay, then one may infer that this dust is coming from something, from the collision of something that might be larger bodies, whether they're planet or Kuiper belt objects. Could be both of them. So, but these are very massive, are more massive in terms of the amount of dust than our own solar system, that we see in our own solar system. What we see in our own solar system is a population of dust that is creating the exozodiacal light. So if you look at at our own solar system, you have this this dust on the ecliptic, which is again generated continuously by either comets or collisions between asteroids and things. And this is a much, much lower level than what is seen in debris disks, okay? So it's an extremely low level. And there have been searches for this in exosystems, let's say, in other main sequence stars. And I'm trying to remember, I'm not an expert, I'm trying to remember, I think has been detected at this level, at the level of the solar system, very near the sun in some system. But I'm not an expert. And it's difficult to detect because it's faint even in our own solar system.
So one place where maybe there's, you might expect some correlations there is, if you look in the sort of models of the solar system that we were hearing about today, the sort of violent scattering phase of the giant planets does a lot of damage to the primordial Kuiper belt. So most of those models start with maybe 50 Earth masses of material in the Kuiper belt, and most of that material ends up being ejected rather than collisionally destroyed. So you might expect there to be some correlations between having massive debris disks that can be seen at late times and the architecture of the planetary systems that remain. And people have looked theoretically for what those kind of correlations might be. I think there's no evidence yet that the observations that have been made, basically looking for debris disks around stars with known planetary systems, really give any very clear evidence one way or the other. Another point that's potentially interesting is, is there evidence for Kuiper belts at much larger distances than the sun, which would correspond to very cold debris disks? And there were some claims, I believe, from Herschel observations that such systems existed. I haven't actually followed up really what happened with those because there was some issues about whether some of those could be contaminants by background galaxies. But at least in principle, looking for very cold debris systems is interesting because that sort of says something about the outer scale at which planet formation could take place.
So the question relates to the formation of Mercury, a Mercury-type object in the Grand Tex scenario. Yes, if I remember correctly, what you have also seen there was no Mercury present, or very few objects of Mercury size present there. But the general, let's say, mass distribution they found out allows very well for objects there, I think, in this range where Mercury is located there. So you have a distribution which is a maximum near Venus and Earth, and then it goes down on both sides. So I don't know whether this was just I think they have combined here the results of two different simulations. So I'm not sure whether they couldn't make an additional simulation that produces Mercury there. But the general mass trend, I think, is correct. I think this is the idea. You have in general, statistically, the models give the right answer there. And whether you get in one particular model a Mercury or not, I think this is just by chance. And they have combined here two different models. But I cannot say, I don't know, there are other models, which ones have produced a Mercury and not. But Mercury is very small, so I don't know whether it's really significant that you have it present or not. I mean, if you had a terrestrial type planet, then you could ask, okay, why don't we produce this additional terrestrial planet there? But Mercury, with its very small mass, it could have been easily, for example, be scattered out some time ago, because we know from stability calculations by Jacques Lascar and others that the instability timescale for Mercury is surprisingly short. So it's a big surprise after all that it's still present in our own solar system after all.
I think in the solar system context, a lot of attention is given to the small mass of Mars, and the sort of the motivation for this grand tack. I think given what we now know about the population around other stars, the fact that there is nothing larger inside Venus, is an issue that is also important, right? And I think that's not really something that was addressed with the grand tack. Why, for example, there's nothing in it 20-day orbital periods in the solar system, because those planets seem to be common elsewhere. Something else maybe to note is that when you start getting down to thinking about Mercury, then at least some of the models for that involve collisions that are not purely accretional, and which are so-called hit-and-run type collisions. And so probably there will be more work on understanding the outcome of collisions in a little bit more detail, and it's at least possible that might slightly change our opinion of how the accretion of even Mars may work, because depending where you are, the smaller planets, when you get to the smaller planets, the possibility that collisions don't just lead to pure accretion generally becomes, I think, a little bit larger.
So is there a last question? That seems to be the case. So I think we can now thank our speaker. Okay. So we will thank you.
2 minutes to go still.
Each one is required.
But I mean, it's true. I mean, there's no beam.
We know one, maybe two so-called mega-Earths, so solid Neptune mass planets, and the opposite, we know very small low-density planets, so mini Neptune. Do you have an idea to explain the formation of such planets?
I'm tempted to say that I do, but the time is too short to explain it, and now I'll hand over to Willie.
I think I can also give a very short answer. I think the planets of this type will come out. The statistically likelihood of planets of this kind, I think, is a result that population synthesis models, for example, will give us automatically. I mean, it's clear that there is some formation channel which I'm not aware of now directly will potentially lead to such planets there, but they will be captured by these models there. So this is a generic answer. Sorry for this.
Okay, so I think now we can